Good morning, ladies and gentlemen. We are welcome to our lecture number 5 on Cmen846, which is Advanced Measurement and Instrumentation. Today we'll be looking at spectrum analyzers. The spectrum analyzers, they are signal analysis instruments which are used for observing the amplitude of a signal against the frequency, which means it is carrying out its analysis in frequency domain. But the oscilloscope, as we have seen in the previous lecture, it is used for carrying out signal analysis in time domain. What this means is that in spectrum analyzers, the amplitude of the detected signal or the analyzed signal is displayed on the vertical axis, while the frequency is on the horizontal axis. And the normal spectrum analyzers they have scales in which we have 10 major vertical divisions and we have 10 major horizontal divisions. That is, on the amplitude axis we have 10 divisions, though there may be some, or there are smaller divisions within the main divisions, but we have 10 on the vertical, 10 on the horizontal. And the way we can use the spectrum analyzer to visualize or monitor or analyze the frequency behavior of any signal, we can use what we call center frequency approach. And in this method, what we do is normally to set the frequency of the signal we are expecting, because each system you may have an idea of at what frequency it operates. That's the fundamental frequency, though we can have harmonics that can go higher, and sometimes you can even have frequency below those fundamental frequencies. So if we want to use this center frequency approach, we place the signal at that central point of the spectrum analyzer in such a way that whenever we start to take measurements, it can shoot above that center and it can fall below that center depending on the component of the frequencies available in that system. Then the second method we can use the spectrum analyzer is using the approach of setting the lower and the upper frequencies. In this way, we just take our system, we want to analyze its frequency response, we assume, or we take the possible value that is maximum, we set it, and we set the minimum. So whatever we are going to be visualizing on our spectrum analyzer will be between these two extremes, that is the upper and the lower frequencies. And if you want to carry out analysis using a spectrum analyzer, we have two basic types of spectrum analyzers. The first one is the one that is normally used for low frequencies, that is frequencies up to 100 kilohertz. And this kind of spectrum analyzers, they operate based on what we call the Fourier transform of a signal, or Fourier transform signal. Normally they are called FFT, that is fast Fourier transform spectrum analyzer. And as we have said, they operate at low frequencies up to 100 kilohertz. The other one is the one that uses radio frequencies, which is normally high, or sometimes even microwave frequencies, and these frequencies can range from the upper limits of the other one, which is 100 kilohertz, up to around 100 gigahertz. And this kind of spectrum analyzer, we use the technique of sweeping, and for this reason they are called sweeping spectrum analyzers. Now let us look at these two types of spectrum analyzers. We are going to start with the sweeping spectrum analyzer. The sweeping spectrum analyzer, its operation is very much similar to that of heterodyne radio receiver. And if we can remember, the radio receivers are of different types, and the heterodyne is the one in which when the radio frequency is accepted, it contains two frequencies, we have our intelligence, that's the original message, and we have our carrier frequency. So it will now mix this receive radio frequency with what we call the signal from the local oscillator. In this way, it can eliminate the carrier frequencies and finally obtain the intelligence. Now, in order to understand how this heterodyne approach works, or how this sweeping spectrum analyzer works, we may use this block diagram or schematic diagram, which represents all the components contained in the sweeping spectrum analyzer. Here we assume this is our input terminal where we take our signal to be analyzed, and we first pass it through a series of attenuator and amplifiers. Because there is maximum frequency at which your spectrum analyzer can safely operate, so sometimes you need to use attenuators in a situation where the frequency the amplitude of the signal is too high, much above the safe limit, and sometimes if it is very low, we have to use an amplifier in order to boost it. So after that, we deliver our signal to a low pass filter. Its function is to make sure that it allows only the fundamental frequency pass, and all the overtones are attenuated. Now, when this signal is received now, it will be combined with the signal generated by what we call a local oscillator. And when this local oscillator signal is mixed or is multiplied by the high frequency, which is normally radio frequency, we obtain what we call intermediate frequency. And this intermediate frequency is nothing but the intelligence contained in the radio frequency, in such a way that the frequency from the local oscillator has now eliminated the carrier frequency. After getting this intermediate frequency, the next thing is the detector, which will now be detecting the amplitude of the signal at different frequencies. And we use a filter also in order to make sure that the range of frequencies allowed, they are the only ones passed. And finally, we display our waveform on the screen of the spectrum analyzer with the frequency on the horizontal axis and the amplitude on the vertical axis. So if we look at this one, is just the explanation of what I've just said. As I said, we have attenuators and we have amplifiers for either reducing or raising the amplitude, as the case may be. And we have a mixer. The function of the mixer is to mix the radio frequency received, or the input radio frequency, with the signal from the local oscillator. And we also have several stages for conversion, and these conversions, they are made in such a way that we can allow only the range of the allowed frequency to reach our next stage. All the other high frequencies are attenuated. And also, each mixer, as we have seen in that diagram, it has a local oscillator, and the local oscillator is the one that gives us the intermediate frequency, after which we pass it through a filter again. And now, sometimes we use digital filters at the final stages before we display our frequency or the waveform on the spectrum analyzer. And also, these digital filters, they are very important in enhancing the stability, especially when you are dealing with very low frequencies as low as 1 Hz. Now, after the filter, we now pass it through a detector, as I've already explained, in order to detect the amplitude at the different frequencies, and finally we display it on the screen of the spectrum analyzer. Now, whenever you want to use a certain device, whatever it is, there is need for you to be able to control some parameters in order for you to get the required results. And what are the parameters that we can regulate in spectrum analyzer? Basically, we have 4 of them. The first one is the central frequency, you can always regulate your central frequency on the scales of your spectrum analyzer, and you can also regulate the span of the frequency. What we mean by this is the difference between the lowest and the highest frequencies, and also you can regulate the resolution. And in this case, the resolution is nothing but the length of the selective filter or the bandwidth of that selecting a selective filter. What is the lowest frequency it can allow, and what is the maximum frequency it can allow? We can always design our filter to suit our own requirement. And the last parameter we can regulate is the sweep rate. Now, this resolution, or the bandwidth resolution or resolution bandwidth, and the sweep rate, they are connected by this mathematical formula. That is, the sweep rate is equal to the square of the resolution bandwidth over by kf. This kf is a constant depending on the type of filter we are using. If you are using Gaussian filter, this kf is approximately equal to 2. Now, if you detect your amplitudes of the signal on the analysis against various frequencies, you can always adjust that amplitude using different methods. And these methods, the first one, we can regulate that amplitude, or we can adjust that amplitude using what we call the reference. And what is the reference? The reference is nothing but the maximum value which is displayed on top of our screen. We can always adjust it in such a way that it can cover a wider range or space on your screen of the spectrum analyzer. The next thing you can adjust is the units in which you are carrying out your measurements. And also you can adjust the scale. The scale, as we know, is nothing but how many units per division. You can always adjust that. By doing that, you can adjust your amplitude of the signal so that it can cover either a wider range or a smaller range. And one of the parameters we said we can adjust is the unit. So what are the units that are normally being used for carrying out analysis of signal in spectrum analyzer? There are two. Sometimes we make our measurement in volts. That is, the amplitude on the vertical axis is in volts. And it can be multiples and sub-multiples of that volt. It can be millivolts, it can be kilovolt, it can be any other thing depending on the amount of the amplitude you have in your signal on the analysis. And the second unit we use for measurement in spectrum analyzer is the dB, that is the decibel. And this decibel also, it has some other different variants. We have dBm, we have dBV, and so on. And always this one is used when you have a signal that has a very large amplitude, because when you are using dB, you are expressing your results in logarithm, and taking the logarithm of number is always suppressing it. For instance, if you take the logarithm of 10 to base 10, it will give you only 1. The logarithm of 100 base 10, it will change to 2. The logarithm of 1000 base 10, it will be 3. Meaning, whenever you express something in decibel, you are maximizing your space by compressing your amplitude to be displayed. And this spectrum analyzer, which we call is the sweeping type, the sweeping, it can be done in different ways, but the most commonly used method is using analog voltage control oscillators. Now let us look at the second type of the spectrum analyzer, that is FFT, fast Fourier transform analysis or analyzers. And for us to understand how it operates also, we look at the block diagram or the schematic diagram. As in the other case, we have an attenuator. In the case where amplitude is too high, we can also have an amplifier where the amplitude to be analyzed is very small. After that level, we deliver it to our filter, which is analog in nature. As we know, the function of the filter is always to what? Remove certain range of frequencies that are not allowed, normally harmonics or overtones. Now after that, we go to the level of sampling, because in this one you have to change your analog signal into the digital form. And the first stage we do in changing analog signal to digital is to take samples. After that, to take samples, and taking the samples is normally done using what we call sample and hold circuit, and this represents a sample and hold circuit. After taking the samples, we now come and change those discrete values into digital values, digit zeros and ones. And how do we achieve that? We go to the next stage, that is quantization, where we change those discrete values into numerical values. After that, you pass your signal, that is the digitized signal. It has to pass through a filter again before you deliver it to the level where we take the Fourier transform of the signal, and finally it is displayed on the screen of your spectrum analyzer. And all these things that follows, it is trying to explain what I have just said. As we have said, we have attenuators. Sometimes it can be amplified depending on the nature of the signal. We also, the reason why we do this filtering after the attenuation or amplification, as the case may be, is to avoid the problem of aliasing. What is aliasing? Whenever you want to digitize a signal, there is what we call the sampling frequency. And according to the Shannon's-Nyquist theorem, it says the sampling frequency must always be at least twice the maximum frequency in your analog signal. So now, if you don't use a filter, you may encounter a problem, because if the fundamental frequency of the signal, let's say, is 10 kilohertz, and you don't know that harmonics exist, the harmonics are multiples of that fundamental frequency. Maybe let's say the second harmonic, maybe that is 3 times or 2 times the fundamental frequency. Let's say it is 20, but we know the original signal is supposed to have only 10 kilohertz. Kilohertz. Now, whenever I want to sample this, that 10 kilohertz, if I check my sampling frequencies to be 20, I obey the Nyquist-Shannon theorem. But I don't know that we have multiples of that as a result of what? Harmonics. And that will cause aliasing. That is failure to reproduce the original signal whenever you are changing it back to the analog form. Then, as I have explained, after this filtering, I'll go to my sample and hold circuit. And after that, I'll go to the quantization, that's the ADC level, where I change those samples discrete values to numerical values. And finally, I'll filter it before I deliver it to my FFT, that is the Fourier transform circuit. As I have already explained, whenever you are sampling, you have to obey Nyquist criterion, and it says the sampling frequency must be greater than or equal to twice the maximum frequency of the analog signal. Now, one important advantage of this FFT analyzer is that it is very high in its operation. Why is it having high speed? The reason why it has high speed is that it can establish all the components of the signal within one time, meaning it doesn't need to look at different components at different times, but it can combine all of them and process at the same time. So this makes it faster. Okay, whenever you have FFT spectrum analyzer and the sweeping spectrum analyzer at equal resolution, you find that the speed of the FFT is much above that of what? Sweeping spectrum analyzer. And another advantage it has is that it has a good resolution even when it's operated at low frequencies, though we always said it is operating at a higher frequency. Now, where are the areas? What are the major areas where we apply the spectrum analyzers? We have different areas. The first one, we use spectrum analyzers to carry out spectral studies or spectral analysis of oscillators. That is, to know the amplitude of the signals in an oscillator at different frequencies. And sometimes it can even analyze the spectral qualities or behaviors of modulated signals like AM, that is amplitude modulated signals, or FM, frequency modulated signals. And the studies of these oscillators or modulated signals, it helps us to establish what we call the spectral dimension around the carrier frequency. That is, if you have your carrier frequency, whenever you have the envelope, if you can remember, it keeps on changing from the lowest value to the highest value. So you can now analyze and see, okay, at those center frequencies, what is the amplitude? As frequencies goes above the center, what do we have? As the frequency go below the center, what do we have? So another place where we apply the spectrum analyzer is we use it for analysis, or sometimes, yes, to analyze the modulated signals, because the first one here we said it can deal with what modulated AM or FM. Sometimes we can have spectrum analyzers that can demodulate the RF signal before it now analyze it as spectral behavior. We also use spectrum analyzers for carrying out analysis of the amplifiers. And the amplifiers, as we know, we have different types. Okay, so we can use spectrum analyzer to analyze and see what are the amplitude of the signal at different frequencies. And finally, we use spectrum analyzers to carry out analysis of what we call harmonic distortion. As I told you, if you have a circuit and you know the frequency it should operate, that frequency we call it the fundamental frequency. But sometimes multiples of that frequency may exist without your knowing, and those multiples we call them harmonics. Okay, in some cases we have what we call overtones. So these harmonics, they are a kind of distortion to a circuit. So we use a spectrum analyzer to analyze and see what are the amplitude of the signals in those multiple frequencies, that is harmonic frequencies. Then this harmonic distortion analysis, it helps us to know what are the frequencies or what are the amplitude of the signal in the harmonics as compared to those in the fundamental frequency. And when these kind of measurements are carried out, the signal in the harmonics as compared to those in the main fundamental frequency, they are expressed in percentage, meaning we'll say so percent are in the harmonics while the other energy is in the fundamental frequency. The higher the percentage we have in the harmonic, the worse the behavior of the circuit will be. And if we discover that, then we can carry out some adjustment to the circuit in order to reduce the presence of the harmonics and the amount of energy contained in those harmonics. And another way or another place where we use the spectrum analyzers, we use it when we want to carry out analysis of power spectral density. And this power spectral density is nothing but a method of or a process of normalizing the amplitude of the signal per unit frequency. That is, we should say whatever is the amplitude. As I told you, we can use voltage as our unit on the vertical axis, and sometimes we use decibel. So when you want to find power spectral density, you will say whatever is the amplitude divided by total frequency. So we always express that power spectral density either in volt per hertz, that is when our unit is volt, or sometimes in dB per hertz when we are using decibel as our unit. And we also use spectrum analyzers if we want to carry out measurements of phase noise in oscillators. You know, oscillators are of two types. Some of the oscillators, they are supposed to operate in phase, that is, the angle at which the output reaches maximum and fall to minimum is always constant. And we have some oscillators that are called phase shift oscillators. Okay, So when you design oscillator to operate in phase, you can always use spectrum analyzers to visualize and see the values you are getting, that's the amplitude, always at the same frequency. If yes, then it is in phase, and if not, you can find out that there is a phase shift where it is not needed. That is a problem. Okay, this phase shift noise analysis, it help us to find what we call the spectral purity of the oscillator or the sharpness of the oscillator. If the phase angle is equal to 0 where it is not needed, then definitely the spectral purity is very high, and otherwise we can say the spectral purity is very low, or it has problems. Now, whenever you want to use spectrum analyzers for carrying out measurement, there are some hints you need to know, and these hints are of different types. The first one is you need to be able to adjust the gain of the spectrum analyzer so that you can get accurate results. And how can we adjust the gain of the spectrum analyzer? We can do it in two ways. Either to use what we call RF attenuator, and this RF attenuator is nothing but a circuit that will receive an RF signal and try to reduce its amplitude so that we can have a safe value of amplitude entering our spectrum analyzer. Otherwise, when the amplitude is very high and it goes beyond the safe limit, it can cause damage to the spectrum analyzer. The second way we can adjust our gain is using what we call if gain, that is intermediate frequency gain. As we have seen in the spectrum analyzers, we talk about intermediate frequency, especially when we discuss about sweeping or spectrum analyzer. And if you control the level of this gain within the if stage, it can help you get a safe amplitude going into your spectrum analyzer. Therefore, it is safe from any damage that may happen as a result of too much or a very high amplitude. Then the next thing we can do is, let us look at the filter bandwidth. As we have seen, at different levels in the spectrum analyzers, we use filters, and we said the function of these filters are to remove any harmonics that are together with the fundamental frequency. Okay, so how do we determine the bandwidth of the filter? The bandwidth is nothing but the range of frequency that the filter can allow to pass. Okay, so we have two ways in which we can control the bandwidth of the filter, or we can adjust it. The first one is the intermediate frequency bandwidth, and this intermediate frequency bandwidth, it is nothing but the resolution bandwidth. What we mean by the resolution bandwidth, that is the amount of, or the range of frequencies that are allowed to pass through our IF filter after it passes through the local oscillator, and it helps to adjust the resolution of the spectrum analyzer in terms of what frequency. Then the second way we can adjust the filter bandwidth apart from the if bandwidth is the video bandwidth. The spectrum analyzer always is displacing an image, a graphic representation of the data on the screen. So the video, because it is now visual, okay, if you have your video filters, they will enable you to be able to express your signal in terms of average. And whenever you are taking average, there is every tendency that it should not shoot beyond the limit, or it should not go far below the limit, because you are taking everything and dividing to the number of the things you've connected together. Now, the next thing we need to talk about is the scan rates. The two types of spectrum analyzers we talk about, we have sweeping and we have FFT. Okay, so this scan rate, how does it affect the operation of the spectrum analyzer? So the scan rate, the first thing we need to know about it, it is the rate at which we are scanning the signal in the spectrum analyzer. That is how many times are we detecting the amplitude at different frequencies. And this scan rate, the faster it will be, the better the operation. Why? Because whenever the scan rate is very slow, it will take a longer time for a measurement to be made, which means we always need to find a way of increasing the scan rate. And we have different ways that we can increase our scan rate. Okay, and we said it is advantage. If we raise it, it is advantage because it will be taking measurement faster. But one thing we need to remember is that even though increasing the scan rate is good, but this spectrum analyzer is limited by number of factors. Meaning, before you can increase the span rate, there are some factors that limit your ability to increase it indefinitely. The first one is the bandwidth of the if filter, that is intermediate frequency filter. Whenever the bandwidth is narrow, definitely the filter should be what? Slower in response. So it means whenever I want to increase the scan rate, I have to make sure that the bandwidth is what? Wider, so that my scanning should be wider also. Also, the bandwidth of the video filter. Whenever the bandwidth of the video filter is small, then the scan rate should also be slow, which means you need to always increase the bandwidth of the video filter if you want to be scanning at a faster rate. Then this scan bandwidth also is another parameter that limit our scan rate. And what is the scan bandwidth? It is nothing but the bandwidth of the signal that we want to analyze. What is the lower frequency and what is the higher frequency? Whenever that frequency increases, then it is proportional to the scan time. What we are saying here is whenever you increase the scan bandwidth, it will be taking a longer time for a scanning to be taken. So as we are trying to increase the if filter bandwidth, the video filter bandwidth, in order to increase the scan rate, then the scan bandwidth now has a problem. Whenever you make it high, definitely you will be taking longer time before you can take measurement. Okay, so as we have maybe said, the analyzers are always operated using integrated circuits or processors. Okay, so whenever you try to use a processor with a very high rate of scanning, there is another problem of generating heat. So if you look at all these factors, it means you have to do what we call trade-off optimization. Try to increase the scan rate to a safe value, because if you go beyond that, one of the problems is heating, and heat always is one of the reasons why electronic systems are being destroyed. Now, there are some hints we need to have whenever we want to use a spectrum analyzer safely. The first thing is we have to be very careful about the input level. When you make the input level very high, beyond the level that your spectrum analyzer can take, it can be overloaded, and overloading always causes damage. Then sometimes if you are taking measurement, you observe that some spores, that is some distortion in the waveform, exist. You need to find out, are those distortions from the equipment you are testing, or they are generated by your spectrum analyzer? If they are generated by spectrum analyzer, you have to quickly stop the measurement and take corrective measures. If not, problem will happen. The next thing is you have to wait for the self-alignment. That is, whenever you are using spectrum analyzer, when you switch it on, just like your system, it will boot. After booting, it will go and calibrate some part of it in order for it to take accurate measurements. Okay, finally, for the power measurement in the spectrum analyzer, we should know that the accuracy is much lower compared to the ordinary power meter that could be used easily. So at this point, we have talked about spectrum analyzers, and our next lecture will be looking at automatic test equipment. Thank you very much. Till we meet in the next